So in this section, we're going to talk about graphing, and we're going to specifically look at how to graph an exponential function. We'll look at logarithmic functions in the next section. So when you look at an exponential function, it is simply a new parent function. Like we learned in the fall, we learned about quadratics and absolute values and square roots. And those have a set group of inputs and output points that we call key points. Well, the key points of an exponential, let's see how they're made, right? We have an input, right, and an output. We typically call that, an x and a y, or in this case, an x and an f of x. And what we're going to do is we're just going to focus on the x-axis, -2, -1, 0, 1, and 2. We could go the whole way, but once you get the shape, that's what matters. So I'm just putting the -2, the -1, the 0, the 1, and the 2 in from values on the x-axis. So in f of x, when I put -2 in there, it would go in here in the exponent. That's what makes it exponential. And so I would have 2 to the -2, and then 2 to the -1, and then 2 to the 0, and then 2 to the first, and then 2 squared. And a lot of times it makes more sense actually for students to start at the bottom of this chart. 2 squared would be 4, 2 to the first power would be 2, and of course anything to the 0 power is 1. So what does that negative exponent mean? Remember, negatives mean opposite in math. So what that negative exponent means is that I'm going to have 2 to the first, but it's going to go on the denominator. So it'll actually be down here, and the placeholder for that is a 1. So 2 to the negative first is a half. So this would be 2 squared, which is 4, with the placeholder of 1. The 1 is in the numerator for the same reason that this is 1, because each of these problems has a 1 as a coefficient. So if I have 0 2's, I have a 1 left over. If this goes to the bottom, there would be a 2 there. If this goes to the bottom, it would be 2 squared. Just keep in mind that all functions have a coefficient of 1. Remember, 2 is not a coefficient. In this case, it is a base. All right, so when I graph those points, right, they make this curve. At -2, I have a fourth. At -1, I have a half. At 0, I have 1. At 1, I have 2. And at 2, I have 4. And many teachers, they'll make you do all of those as your key points. I only focus on what makes this curve upwards or downwards, because that could happen depending on the base. So I only really focus on these 3 points to show this curve. So the key points that we use are -1, okay, as you can see over here, -1 produced the base. Let me get rid of this coefficient so it's a little more obvious. -1 produced the base of that number, but on the denominator, okay? So what you're going to have here is you're going to have -1 will always produce 1 over your base, okay? So if this were a 3 to the x, this would have been a third. If this were 4 to the x, it would be a 1 over 4. What if the base was a fraction? Let's say it was 1/2 to the x. Then it would be 1 over 1/2, and it would reciprocate and become 2. And that's what actually causes decay, because it starts large and will then get small. Okay, anything to the 0 power is 1. So this, no matter what function you have, this is 1. You can see it right here, right? So 0, 2 to the 0 is 1. And then 1 would be the base. So again, if I had 3 to the x, this would be 1, 3. If I had 4 to the x, this would be 1, 4. If I had 1/2 to the x, this would be 1, 1/2. So that's how the key points are made for exponentials. They're -1, 1 over base, 0, 1, and 1 base. Now, that being said, these are 3 key points. We're kind of used to having 5 key points, but 3 is enough. And the key points for exponentials, they change every problem, unlike the problems we learn with, quadratics and cube roots. Those are static key points. And again, the key points here change. Okay, so the other things that are important about exponentials is they always have a horizontal asymptote at y equals 0. That will be shifted by the k value, which we'll remember that in just a minute. There is always a y-intercept of 0, 1, okay, no matter what the base is, because if you raise anything to 0, it's 1. The x-intercept does not exist unless the graph has been shifted. Obviously, if I take this graph and I move it around, I have an x-intercept. But the basic graph, the base graph, does not have one. The domain of every exponential graph is negative infinity to infinity, and the range of every exponential graph is 0 to infinity. So remember how we would get that. Negative infinity to infinity is showing the domain, but the range, nothing, 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 beep, and it started beeping after the asymptote. Now that also modifies our end behavior. Remember, the end behavior is simply the domain written in a column, so negative infinity to infinity, and then expressing what aspect of the range corresponds to the domain. So at negative infinity, that arrow is going to the asymptote always. So the end behavior will go to the horizontal asymptote on one side, but on the other side, it's free to go up or down. The original graph at infinity, you can see that it's going to infinity. But keep in mind at negative infinity, this is going to the horizontal asymptote. So as x goes to negative infinity, it goes to 0. As x goes to infinity, f of x goes to infinity. So what else do we need to worry about? Well, we need to review our transformations. Okay, so this is what the graph looks like in its transformational basis. A is still a multiplier of outputs. It could cause a reflection over the x-axis if it's negative, and it can also stretch the graph vertically. B is going to provide these key points. So these key points are going to be modified by B. And you might be used to seeing a B here, but that B, it could be there, and you still would have to GCF factor it. But that B would actually change the key points. So it's not as critical in exponentials as it was in the fall, but it will matter with logarithms. But for now, make sure you modify your base to figure out, make sure you use any coefficient in the exponent to modify the base to find the key points, and that takes care of it. Once you have done that, the H will translate the graph left or right. This does not affect the asymptote at all, because if I take this horizontal asymptote and move it left or right, it's still at 0. But what's going to affect it is if it moves up and down. In fact, the K value is the equation of the horizontal asymptote. K moves the graph up and down. That's going to change the horizontal asymptote. In fact, y equals K is the equation for the horizontal asymptote. And you'll see that in the examples when we look at them. So just a review of everything we talked about. If the absolute value of A is greater than 1, the multiplier in the front, the graph will stretch vertically. If it's between 0 and 1, meaning a fraction or decimal between 0 and 1, it's going to compress the graph. Remember, A is a multiplier, so if I multiply something by a half, it gets smaller. And the reason there's an absolute value here is because the negative on the A actually does something separately. So that's just notation. If you had negative 1/2, it would reflect over the y-axis and compress vertically. Keep that in mind. B it does do this, but it does it in a different way by changing the key points. This is going to be very important when we look at logarithms. And the vertex, of course, is going to be h comma k, but remember that h is always opposite. H is still negative. So if you actually solve in here an exponent of like x minus 3, h is actually 3. And if this is positive, it becomes negative 3. So when h is negative, the graph is going to translate left. When it's positive, it's going to translate right. H is always the opposite value. When k is negative, it's going to go up and down, changing the asymptote, changing specifically the horizontal asymptote. And when it's negative, it'll translate down, and positive, it'll translate up. Remember that k is exactly what you see, and h is the opposite.